In this example, we're going to find the interval of convergence for the series n equals 1 to infinity of n to the 6th times x plus 5 to the nth, all divided by 7 to the nth times n to the 20 over 3. The first thing I want to do, since this is kind of messy, I want to try to clean it up the best that I can to really see what I've got here. So I'm going to combine the n to the 6th with the n to the 20th divided by 3 by dividing and combining the n's using our exponent rules. What I'll be left with is n to the 2/3 in the denominator. The next thing I want to do is, since x plus 5 to the n and 7 to the n have the same exponent, I'm going to take both of those expressions, x plus 5 and the 1/7. I'm going to combine them together and write that all to the power of n. And then we just have to make sure we include the n to the 2/3 by multiplying by 1 over n to the 2/3. Now we have this cleaned up. It's going to be a little bit easier to see what's going on. So we're going to use the ratio test to find the limit as n goes to infinity of the nth plus 1 term divided by the nth term, all inside absolute value. So let's scroll down here a little bit. Okay, so I'm going to take the limit as n goes to infinity of the nth plus 1 term. Here's the nth plus 1 term. And then I have to divide by the nth term, which is basically just taking the reciprocal of an. So that's this part here. And we just have a big algebra mess here that we have to clean up. So I'm going to take the limit as n goes to infinity. I have an x plus 5 to the n plus 1 here, and I have an x plus 5 to the n here. So I have one more x plus 5 in the numerator than I do in the denominator, so I'm just left with an x plus 5 upstairs. Same thing goes with the 7. I have a 7 raised to the n plus 1 downstairs, and I have a 7 to the nth upstairs. So I have one more 7 downstairs than I do upstairs, so that's going to stay down here, a 7 to the 1st. Now, there really isn't anything I can do with these because they have different bases, so I'm just going to carry those down. This term right here, since it doesn't have any n's in it, I can pull it outside, and I don't need to put absolute values around this term here because n is going to be 1, 2, 3, 4, 5 in the positive direction. So we're not going to get negative values here. So when I take the limit of this expression as n goes to infinity, this is going to approach 1. So I'm going to be left with x plus 5 over 7 absolute values, and then times 1. So in order for the ratio test to say that this converges, our limit needs to be less than 1. So I'm going to take x plus 5 over 7 in absolute values and set up an inequality and say that that's going to be less than 1, which means x plus 5 is going to be greater than negative 7 or less than positive 7. And when I subtract 5 from all three pieces of this compound inequality, I get this inequality here where I have x has got to be between negative 12 and 2. Now, the ratio test is inconclusive when the limit is equal to 1. So I need to test when x is equal to negative 12 and x is equal to 2 separately. So I'm going to go back up into the original series, and I'm going to plug in x is equal to negative 12 and simplify it, and this is what I get. So if you use the alternating series test on this series, you're going to find that this converges. So the series converges when x is negative 12. When I go back up to the original series and plug in x is 2 and I simplify it, this is the series that I get, And we know that based on our knowledge of p-series, this series is going to diverge because this p is less than 1. So when we write out our final interval for the interval of convergence, I can include -12, but I'm not going to include x's 2. So this is going to be my final interval.